Today we're going to be looking at intermolecular forces. So to begin, I just want to quickly look at states of matter, and the reason this is because intermolecular forces actually help us understand why certain chemicals are the state of matter that they are at room temperature. Understanding the intermolecular forces helps us understand the bulk scale properties of these compounds, of these molecules, of these elements when they're at room temperature. So really quickly, just reminding yourselves that the particles of a solid are rigid in place. They have a little bit of vibration, but they have no flow. Particles of a liquid have a little bit of flow, have the ability to flow, but are still right next to each other. And then particles of a gas are infinitely far apart from each other. They are bouncing off the walls, or bouncing off of each other, etc., etc., etc. So why is this? What causes certain particles to be more attracted to others, while others seem to be not attracted at all? And once again, our answer, our reasoning for this is going to be intermolecular forces. So let's actually get into this. Intermolecular forces, which is often abbreviated as IMF. First off, the prefix inter means between. Inter means between. So we'll often hear the interstate freeways, like the Interstate 5, the I-5, refers to going between states. So the I-5 goes between California, Oregon, and Washington. So intermolecular forces are going to be forces of attraction between particles. And I think one of the most obvious examples of intermolecular forces that we have and that we've discussed about is water. So remember, water is this polar molecule. Water is this polar molecule. And polar has to do, remember, with an electronegativity difference between the oxygen and the hydrogen. The hydrogen is slightly positive, delta positive, and the oxygen is slightly partially negative, and this is due to the fact that oxygen is more electronegative than hydrogen. So the intermolecular force arises between two water molecules. So if I bring in another water molecule here, and this other water molecule, remember, is going to have the lone pairs like this, etc., etc., will also be slightly negative on the oxygen and slightly positive on the hydrogen. And what do opposite charges do? They attract, and this force of attraction right here, once again, is called an intermolecular force, And there are going to be three types of intermolecular forces that we're going to look at and define today, okay? So prior to doing this, though, let's just remind ourselves a couple of things that are going to be important for this. First off, electronegativity. Electronegativity refers to the ability to attract electrons in a chemical bond. Electrons in a chemical bond. And the element that is most electronegative is fluorine here. The element that's the least electronegative is francium down below. So just remember that our electronegativity increases as you move up and to the right on the periodic table. It doesn't include these noble gases here, though. So fluorine is the most electronegative, while francium is the least. And we use this to help identify if an entire molecule is polar or not. So remember, a polar molecule is going to be a molecule with a distribution of charge. A distribution of charge. And what this means is that part of the molecule is going to be slightly negative while the other is slightly positive. So part is positive while the other part is negative. And this has everything to do with the fact that there's an electronegativity difference. Due to an electronegativity difference. So for example, if we were to look at water one more time, I'm going to draw water in a slightly different way here. The oxygen, which is further to the right and up on the periodic table, is going to be more electronegative than the hydrogen is. So essentially what we have here is a net negative pull towards the oxygen and a net positive on the hydrogen. So once again, another way we can kind of depict this is with this arrow, where the arrow points towards the more negative end, or with these delta signs, these lowercase delta signs, which represents the hydrogens as being slightly positive and the oxygens being slightly negative. Polar molecules will absolutely exhibit intermolecular forces. So without further ado, let's go ahead and look at some examples of polar molecules and intermolecular forces, these force of attractions that exist between molecules. So the first one that we're going to look at here today is the dipole-dipole force. This is going to be the force of attraction between polar molecules. Now, as we saw above, water is a polar molecule, so it has a type of intermolecular force called the dipole-dipole force. So let's use a different example here. We're going to use HCl. So when we draw out the Lewis structure for HCl, there's a single bond between the hydrogens and the chlorines. And because chlorine is further up and to the right than hydrogen is, chlorine is going to be slightly negative. It is more electronegative than the hydrogen. And so therefore, the electrons in this chemical bond right here are going to be more attracted to the chlorine, making the chlorine ever so slightly negative. What this means is that if I were to bring another HCl molecule, which of course in a sample of HCl have billions of them, it will orient itself such that the hydrogen is near the chlorine, and that's because opposite charges attract. The force of attraction is called an intermolecular force, but this specific intermolecular force, remember, is a dipole-dipole force. So this intermolecular force, which attracts this entire molecule to this entire molecule, is called a dipole-dipole force. Now, a really specific type of dipole-dipole force is actually called a hydrogen bond. Now, the first and most important thing is to note that a hydrogen bond or hydrogen bonding is not a chemical bond. Hydrogen bondings are super important in the world of biology, and what's important to note with this is that it's going to be the attractive force between molecules with hydrogen bonded to fluorine, oxygen, or nitrogen. It's kind of silly, but it helps us remember. Hydrogen bonding is fun. So, for example, water is an excellent example of a hydrogen bonding molecule, a molecule that will hydrogen bond to another molecule. And the reason that we need this very special definition is because hydrogen bonding is just stronger than dipole-dipole. However, I do want to point out it looks exactly the same. So let's go ahead and look at hydrogen fluoride, HF. Now, when I draw this, you're going to start thinking, hey, didn't you just do pretty much the same thing on the slide before? And the answer is, yeah, pretty much. Fluorine is more electronegative than hydrogen, so it's going to be slightly negative. And hydrogen being less electronegative is going to be slightly positive. In a sample of hydrogen fluoride, I'm going to have billions and trillions of molecules, and they will all orient themselves such that the hydrogen of one molecule will be near the fluorine of another molecule, and this attractive force right here is a type of intermolecular force called a hydrogen bond. And once again, a hydrogen bond is just a stronger dipole-dipole force. The reason that is because fluorine, oxygen, and nitrogen, are very electronegative. So therefore, they can actually remove the electrons from the bond better than other elements can. And therefore, the intermolecular force between hydrogen and fluorine of different molecules is actually quite strong. Now, the last type of intermolecular force is really interesting. It's really cool. It's called the London dispersion force. Now, as far as the London dispersion force goes, it's important for us to understand that even molecules that don't have a polar moment, a dipole moment, can exhibit attractive forces between themselves, and that's because all molecules contain charged subatomic particles. So London dispersion forces are going to be the force of attraction between nonpolar molecules or the noble gases. And once again, if we're kind of using this as a context for states of matter, we can identify that things like liquid nitrogen or dry ice, which are both composed of nitrogen and carbon dioxide, they can exist in states of matter that particles are still very attracted to each other, and this is solely because of these London dispersion forces. What essentially happens is particles develop an instantaneous dipole when they induce a dipole on a neighboring particle. Basically, the London dispersion force has to do with the random motion of electrons, due to the random motion of electrons. And because of this statement, we also know that more electrons means a stronger LDF, London dispersion force. Now I just want to illustrate once again what this London dispersion force kind of looks like. If we have a molecule where the electrons just so happen to unevenly distribute themselves, they're like more on the left side of this molecule because they are moving, they're mobile. What this would do is it would actually cause an attractive force on another helium molecule's electrons, causing them to kind of force over to the left-hand side here. And what this would do is it would induce a dipole in a neighboring He atom. Now, helium being very small, helium has very, very, very weak intermolecular forces and very, very, very weak London dispersion forces. So it's important to note a couple things. The strength of intermolecular forces helps us predict some bulk scale properties of these molecules. So what we want to know is that hydrogen bonding is relatively the strongest. And the reason I say relatively is because it can be weaker than other types of intermolecular forces. But generally speaking, if I notice that something has hydrogen bonding, I can make the claim that it will probably have the stronger bulk scale properties. In the middle is the dipole-dipole forces. And last but not least, we have the LDFs. LDFs are considered the weakest. And this is for, once again, when we are predicting the bulk scale properties of compounds. Now, with that being said, there can be incredibly strong London dispersion forces. For example, waxes, the particles in wax are very attracted to each other, and this is And the evidence for this is the fact that wax is solid at room temperature. However, the strongest intermolecular force between particles is quite literally just the London dispersion force. Now, I've mentioned a few times bulk scale properties, so I'm going to quickly define what each one of these kind of is for us. So first off, the stronger intermolecular forces means that we're going to have higher melting and boiling points. Higher melting points and boiling points. Now, with these melting points and boiling points being higher, the particles are very attracted to each other, so they don't want to exist in the liquid or gas phase if they have strong intermolecular forces. If the particles are really attracted to each other, they're going to prefer to exist in the solid phase. Whereas particles that have maybe weaker London dispersion forces, they're going to exist in the gas phase. For example, the noble gases. They'll have higher viscosity, and viscosity just refers to the resistance of flow. To flow. Things that are going to be viscous are going to be like maple syrup or molasses. And last but not least, stronger intermolecular forces means the substances will have higher surface tension. And surface tension refers to the resistance to an increase in surface area. Wonderful. So now that we know a little bit about intermolecular forces, our next lesson will be able to identify what type of molecules have what types of intermolecular forces. Thanks, y'all. Have a good day.